Section 13.2, line integrals, video 13, versions of a line integral of a vector field. In the previous video, we somewhat painstakingly went through the Riemann sum approach to figure out what the integral of a vector field over a curve looks like. And it was the integral of the vector field dot the unit tangent vector. This is assuming that you have some position function r of t. Integrate with respect to the arc length parameter s. But just like the line integrals we did before, sometimes it's easier to boil it down to an integral in terms of x or y, or some parameter that defines the curve. So let's say that we have a position function rt that's defining the curve over which we're integrating, and let's say that this is valid over the interval a to b. In other words, our curve begins wherever we get when we insert a into the position function, and it ends where we insert b. Then how could we write this in terms of something we can actually integrate from a lower limit to an upper limit? And it shouldn't surprise you that those limits will be a and b. Well, let's think about how to transform this completely into terms of t. Now, the vector field can just be evaluated at wherever that position function puts us. So we can just say that the f is just f evaluated at the position function. And when I say this, I mean the vector field evaluated at xt, yt, zt. Because remember, the vector field is just a function that says, give me your three inputs and I'll return a vector. Well, in this case, the three inputs would be the component functions of our position. We've written it in previous videos, but we haven't in this video, so I think it's worth mentioning that we are assuming that the position vector function, rt, is equal to xt as the component function of I, plus yt as the component function of j, plus z of t as the component function of k. So we are still working under that assumption. All right, so this will give us our vector field, our force, if you will, as a function of t. But what about the unit tangent vector? I know it kind of sort of is a function of t, but really it's a function of r of t. Make sure I get all my r's and t's and everything's in the right place. So what is this? This is the derivative of r divided by its magnitude, the magnitude of the derivative. But the only other thing we have to figure out how to trick out into terms of t explicitly is ds. So how are we going to get that in terms of t? Well, the trick to doing that is remembering how the arc length is defined in terms of vectors. Arc length is essentially the magnitude of the function. That's a magnitude, yeah. Make sure I'm setting this out correctly. In other words, if this, I'll make sure I'm setting this up correctly. Yeah. Our arc length is just the magnitude of the position. Yeah, because this gives you the length of a vector, and this is approximately the length of a vector. So if we took the derivative of both sides, we could say ds dt is equal to the magnitude of the derivative. And so if we multiply both sides by dt, we get ds is equal to the magnitude of the derivative times dt. So now we have an expression that can replace the ds. So that means that we can write our function, our line integral, explicitly in terms of the parameter t. So we can evaluate let me move this down, I need some space. We can evaluate the line integral of f dot t ds as the single integral from a to b of f of rt dot the unit tangent vector function, which is the derivative of r over the magnitude of the derivative. So the derivative of r over the magnitude of the derivative times ds, which is the magnitude of the derivative times dt. Magnitude of the derivative times dt. Oh look, the magnitudes of the derivative cancel. So here's version number 2. We can evaluate the line integral by evaluating the single integral from a to b of the vector field, and my apologies, I left the arrow off the f since it is a vector. Evaluated at RT dot the derivative of RT dt. And we can even make this more compact. We can make this more compact by saying if f is equal to f evaluated at RT, which it is, we kind of made that leap over here casually, but we got to put something into this function. Sure, this function's component functions. Let me rephrase that. We have to put something into this vector function. Sure, this vector function's component functions. So we can just capsulize it all the way back down to just vector f. But what about the rest of it? What about this? Well, we can just call that the derivative of the position function. Because how would you take the derivative of the position function with respect to t? You would do its derivative times the derivative of the inside, the chain rule. So we can just call that dr. Then we can abbreviate this as the integral. They put the limits of integration on this one. Nope, they go back to putting c of f dr. So there's 3 ways to view a line integral over a vector field. The way that falls out from the Riemann sum, the line integral over the curve C of the vector field dot the unit tangent vector ds. But evaluating at ds is tricky, so we can transform it exclusively in terms of the parameter t by evaluating the definite integral of the vector field evaluated at the position vector function dot the derivative of the position vector function, all in terms of t's. But we can write this more succinctly by saying all of this we'll just call f, all of this collectively is the derivative of the position vector. All right, so 3 ways to represent this, and all three of these ways are represented in definition 13 on page 769, in case you would just want to get right to it without all the words in between. In the next video, we'll take a look at an example, and I think that might wrap up the section.